what we'll do today is, well, we're celebrating that fall break is coming up. And so, and of course, we have a homework assignment to do today. So what we'll do is give a short cleanup or finish up from the Sturm-Liouville problems, and then we'll spend the rest of the class doing homework discussion and help. And then later on next week, next Wednesday, actually, we'll start some of these application-based problems and do some of those. Okay. So I don't have much more to say. Yeah, we left off last time after solving this heat equation with the radiation boundary condition. We used the Rayleigh quotient to show that we could exclude the negative eigenvalues immediately. We found that the positive eigenvalues were like the intersection of root lambda with minus tangent root lambda. And so these eigenvalues you'd have to calculate numerically. General theory from Sturm-Liouville tells us that there is an increasing sequence of those that tends towards infinity, but you can also just see it from the graph. And then we had something like UTX equals G times Y, G of T, Y of X. The Y of X was something like a sine term or something, but it was like a cosine or a sine. So we just plugged these in. The G was an exponential function, like e to the minus lambda n times t times k. So we added them up, and then we got this, as usual, that the boundary condition f of x was equal to this infinite sum of cosines. So we got or sines. So we got like a trigonometric series for the function. So yeah, that's where we ended up last time. We checked the last video for details. For today, I want to confront a small generalization of what we've been doing. And the idea, I'll get into it with an example. So say that you work some problem like we were just talking about, and you get G times Y, and say that when you separate the variables, the equation for Y looks like this. And you look at this for a moment, and maybe we've got X going from 0 to 1, and maybe we've got that Y of 1 and Y of 0 are 0. So this is close to a Sturm-Liouville problem, but the issue is that it's actually not a Sturm-Liouville problem. So a Sturm-Liouville has to be Ly equals lambda y. And so what's this L? Ly has to be something like minus P times Y prime plus Q times Y. So evidently, this part of the equation is not in the form of negative P times Y prime plus QY, due to the fact that you've got this extra term. I mean, in order to get Y double prime, you'd have to choose P equals 1, and then you have this like orphan term. Yeah, is there a question, or is he just? Yeah. So this is not Sturm-Liouville problem. And I mean, I guess that's not the worst thing in the world. It's not like you can't solve this equation. But on the other hand, there exists this nice theory with Sturm-Liouville problems. So if you've got a regular Sturm-Liouville problem, then you know that you'll have this increasing list of eigenvalues. You know, we've talked about symmetric operator. There's lots of theory that's built up around it that's nice to have. And well, I'll just ask the class, do you remember any technique from like ODE for how you might solve this? So do you remember like Euler's trick? I know some of you have mentioned it before. So for this, there's no characteristic equation, but there is a trick you can do to rewrite this so that it does look like the derivative of something. Yeah, that's right, integrating factors. So Euler noticed that if you multiply the entire equation by what? Does anybody want to volunteer? Like what?
Well, it would have to be something like the derivative is 1 or -1.
Or yeah, the -1 should come out of the chain rule. So these integrating factors always look like e to a function. And in this case, yeah, that's right. Or I guess for this problem, x. So you multiply through by e to the minus x. And then you want to rewrite this in that form. And can you do it? So what should it be? I guess you've got p equals e to the minus x. Y prime is what it is. And you take that derivative. So does that make the signs work out? So when we put the derivative here, we get that. And we put the derivative here, we get that. And so this is now equal to e to the minus x times lambda times y. So this sort of looks more like a Sturm-Liouville problem with p equals e to the minus x. And so then my question to the class is, well, now is this a Sturm-Liouville problem? Or is there another issue?
Does Q have to be non-zero?
No, I think Q is just allowed to be continuous. So I think Q equals 0 is fine. P should be non-zero.
So is it okay if there's an e to the minus x instead of minus y?
Yeah, that's an issue. We've now got Ly equals e to the minus x times lambda y. So fixing this part screwed up that part. And there's not really much of a way around it. Like this isn't going to just magically become a Sturm-Liouville problem, but when you write it in this form, we can actually kind of fix things. So do these have a special name? Like you might call this like a weighted Sturm-Liouville problem. And so what we've done is we introduce a new function that you might call a weight function R of X. And you consider Ly equals R times lambda y, just like we did with that example. And we take R has to be positive. And so in many examples, R will be this integrating factor. So here R is equal to e to the minus x. And probably R has another condition. Let's at least ask that R is continuous. And we want to kind of redo Sturm-Liouville theory. In this way. And so here's the trick. So you can introduce what we call the weighted L2 norm. So if you've got, say, two functions, f and g, in L2, AB. What's so funny? Well, okay, so you're laughing, so I better tell a joke to, like, this little cause and effect thing, but until the joke after the laughter, but we'll go with it. So, and this situation kind of reminds me of it. So here it goes. Let's see if I can remember. So I say, what's green has wheels and hangs on the wall? And you say, a fish. And I say, well, a fish doesn't have wheels. And you say, yeah, but you could put wheels on it. And I say, well, fish aren't green. And you say, yeah, but you can paint it green. And I say, fish don't hang on the wall. And you say, sure, but you could hang the fish on the wall. And did I say, why did I register for this class? No, but that kind of reminds me of maybe the situation, right? Where you've got, this is not actually Sturm-Liouville problem, so you can't solve it the same way, but, well, we could introduce a weighted norm, Yeah, that's right. I had a math professor in college that actually had a green fish with wheels on it on his wall in the office. Right, so we introduce these like new things to handle situations that are similar but not the same as stuff that we know. So you've got two functions that are, say, square integrable. And you can introduce like a new inner product. So the idea is you fix this function R, CTS for continuous, you fix this function R in advance, and then based on that, you create a new inner product. Just to distinguish this from the usual L2 inner product, it's called the weighted inner product. And instead of doing f times g and integrating, you could just do f times g times r dx and integrate that. So you should really think of this as kind of being like the element of integration, and this as being like the integrand. Even though, I mean, obviously I know it's an integral with respect to x, and you have three functions as the integrand. Your perspective is that you're kind of integrating this with respect to that way of measuring on the x-axis. What do I mean by that? Like if you've got some function, then you can integrate it by, remember you chop up the interval from a to b. And you look at the area of each rectangle. Say, look at the ith rectangle. The area of the ith rectangle was height times width, and your height is like approximately f of I. If it's like a continuous function, the height's approximately f of I, and then you look at bi minus ai. But what if you had, and this is like f of I times the length, sort of the length of this interval from ai to bi. But actually there's more than one way to maybe measure an interval. This might be like the probability that you have an event that lands inside that interval. You might want to use a system of measurement like that instead. And there's and so what I'm thinking of is maybe you could do something like you're building up an integral with this integrand, meaning that your areas now really look like sort of the integrand times like r of I times like bi minus ai minus 1. So it's sort of like that's like the approximate length. And that's your approximate height. And if you go on into higher mathematics, you'll learn about this measure theory and ways of measuring things, and you'll get these little density functions that you integrate against more often. Yeah.
Could this like explanation be on a test, or should we just know the interval definition?
The question is, like, am I going to test you on the explanation I just said? And well, my purpose is just to give you intuition and information. So I'm not thinking of necessarily testing that. But if that's just like, I mean, that's not necessarily just permission to ignore everything, but if you do, it probably won't hurt your grade. So this actually is an inner product, and it does induce a norm. So like the norm, weighted norm of f would be inner product of this function with itself as usual. And you can do Sturm-Liouville theory. With this norm. Instead. And all of the statements in that theorem that I said before are still going to hold. So if you have an equation of the form Ly equals R times lambda times y with the usual boundary conditions and with the usual definition of L, and with this being a positive continuous function, then with respect to this inner product, it'll be true that there will still be an increasing sequence of eigenvalues that go off to infinity. It'll still be true that your eigenfunctions the other way, yeah, thank you. It'll still be true that your eigenfunctions are orthogonal, just with respect to this other norm. So if you just change your way of integrating, then this becomes like a density function that gets collected up by the integral, and all the same theory works out. And it'll still be true that this series of eigenfunctions is complete with respect to this norm. Or this inner product inducing that norm. So it's a little bit of an abuse of language, but it is how people talk. I mean, when you're talking about convergence, it's always like with respect to a norm, because this is the way you measure the error, and the error goes to 0. And complete meaning that if you've now got a function f inside L2 AB, so this means that that function will be equal to this sum. Equal in the mean square sense, this series will converge in the mean square sense. But now this Fourier coefficient, it'll have the formula that this is f y sub n over y sub n, y sub n. So you calculate the coefficient with respect to this new inner product. Yeah. The comment was, this kind of looks like a bird. Yeah.
Do we sometimes have an A naught over 2 terms for F, and sometimes you know?
So that A naught, the question is, why do you sometimes have an A naught over 2 term when looking at these formulas, and sometimes you don't? And so that A naught over 2 term is explicitly for the classical Fourier series. So whenever I'm writing down a function like this, it's always going to be I mean, it depends on the setup of the problem. So if you've got a problem satisfying certain boundary conditions, then you're kind of looking at the vector space of functions that satisfy those boundary conditions. And this formula, will always be true. I mean, if R is equal to 1, then this is just the usual inner product. And in the case of classical Fourier series, this formula is true and holds good. But also in that case of classical Fourier series, we can write down those formulas for the coefficients directly in terms of integrals. So just instead of this, you're actually writing down integral from minus L to L. That's in the specific case, you're on a symmetric interval, which we're not necessarily at here. And you'd be writing down minus L to L of f times sine like n pi x over L or whatever it is, and then divided by this number, which would be a constant. So you actually get those formulas. When you calculate that out for n equals 0, then you'll get that the sine term vanishes. So like B0 is 0. And you'll get that the cosine term has this factor of 2 in it. So to sum it up, like with classical, Fourier analysis, you work with the following orthogonal system of functions. You work with something like the number 1, which is cosine 0 times pi times x. Then like your next function on the list might be cosine 1 times pi times x. Then your next function on the list might be sine pi x. Then you might take cosine 2 pi x, then sine 2 pi x, then so on and so forth. So you get this countable infinite list of these functions, right? And then you show that this is a complete orthogonal system. So you show that if you take any two of these, like if you took inner product of sine n pi x, and so here your lambdas are like 0 and 1 and then 2. So you take sine n pi x, sine n pi x, and you get that that's equal to 0, which is the same thing as this integral. And it also works with these two, right? So if you, like any two of them that are not the same. You get that orthogonality. And so then you write that, you want to write this in a series. But this series, 1, 2, 3, 4, 5, 6, 7, is not naturally indexed. So it's kind of easier to, instead of taking k equals 0, k equals 1, k equals 2, k equals 3, k equals 4, it's kind of easier to just take two sums, one for cosine and one for sine, even though it's like a single countable collection of functions. But then you'll notice that, like, if you take sine 0 pi x, if you take sine of 0 pi x, that's just a zero function. Zero function cannot be included in any basis. So it's not part of this orthogonal system. So here you want to start with 0, and for sines you want to start with 1. And so the way you handle that is you just start this series from 1. And then just include the cosine term. Or, include the cosine 0 term. And then you find formulas for all this stuff, right? So an is going to be integral from minus L to L of f times cosine n pi x dx, all divided by integral of cosine n pi x with itself. Inner product. So this is an integral of like cosine squared n pi x minus L to L. And so you actually compute this number, and it's whatever it is, like L over 2. So you get 2 over L here. And this factor is only there so that this formula works for every single n, no matter what it is, whether it's 0 or 1. But Sturm-Liouville theorem is different. Sturm-Liouville theorem is a generalization of this. So Sturm-Liouville theorem says you get this equation, Ly equals y, whereas before the equation was something like y double prime equals lambda y. So here it's somehow a little bit different. And here your sequence, your orthogonal system of function was like cosines and sines. So here your orthogonal system of functions is just given by y1, y2, y3. It's just given in theory. And they could be the Bessel functions, or they could be Legendre polynomials, or they could be whatever. They could be sines and cosines. Or depending on your boundary conditions, it could be sines only if your boundary conditions are 0. Or it could be cosines only.
But the fact that the infinite sum is extra was a result of our convention of numbering the functions starting at 1.
Yeah. So this is the same as that in the special case that like y1 is 1, y2 is cosine pi x, y3 is sine pi x, y4 is cosine 2x. You just write it in this classical way. And it's also in the special case that a to b is this symmetric interval from minus L to L. And Sturm-Liouville theorem says more generally, there's a large class of PDE that can be solved in this separation of variables manner. So it wasn't really important that this was sines and cosines. What was important was that you had a countable collection of functions that you could then add up, and it would converge in the mean square sense to that function. And you always calculate the coefficients with linear algebra, with this formula.
And this doesn't have to be symmetric on its symmetric interval?
This need not be symmetric.
What's symmetric?
It need not be the case that AB is minus L to L, in general. But if you do it like this, then you get these formulas that work every time. So it allows you to teach this to students who don't know linear algebra, because you can just show this formula. But if you do know linear algebra, then this is the formula. It works all the time, no matter what.
It's just that in that case, the denominator is like 2 L over 2.
Well, I mean, in this case, everything depends on this actual list of functions. They don't have to be sines and cosines.
Oh, I meant for like the classical case with sine and cosine.
Yeah, what was the question?
But we get a set formula because
Yeah, you get a set formula because of the sines and cosines, because this interval is symmetric, and that's what gives you that classical thing. So the way I kind of introduced you in class was I said, well, you know, there's these Taylor polynomials, sort of writing the function in the basis of polynomials. And then you could promote that to, well, could I write a function in a basis of sines and cosines? And you can. And then later on, well, you want to solve more PDEs than just y double prime equals lambda y. So we notice large classes of PDE in the biological sciences are modeled with Sturm-Liouville. And so around the 1830s, we got this theory that says, well, at least there'll be some basis of functions that you can do this separation of variables procedure with. So it's trying to open up to you a larger class of things that you can solve. And then at the top of today's lecture, so we noticed that, okay, well, there's even other sort of common sense equations that you can get that are not exactly Sturm-Liouville problems, but they're close to it. And then you introduce this weighted norm, and you still get the same theory. So that's where all that is coming from. So maybe I'll say like a couple more remarks about our example in this context. So we had looked at minus y double prime plus y prime equals lambda y. We want to convert this to this weighted Sturm-Liouville problem and try to get some mileage out of it with 0 equals y of 0 equals y of 1. And so with integrating factor e to the minus x, we looked at the equation e to the minus x, y prime prime equals e to the minus x lambda y. And now you've got weighted function r equals e to the minus x, p equals e to the minus x, q equals 0. So this equation you can solve. I won't show all the details. I'll sort of like let you check this, or we can discuss in office hours. But you should get that lambda n is 1/4 plus n squared times pi squared, and this is for n starting at 1, and you should get y sub n equals e to the x over 2 sine n pi x.
Wasn't our sine inside the, actually it doesn't matter.
It doesn't matter, but this is the usual way of writing Sturm-Liouville problem. Yeah. And so I think you can do this maybe with like ODE techniques, maybe making substitution, like z equals e to the minus, well, do you need substitution or not? Well, so I won't get into how to solve this from first principles. Like maybe you could write this as a system of equations or do a substitution, but just by way of example, I'll give you this solution in the eigenvalues. And then the point is that these really are orthogonal with respect to this weighted norm, because the weighted norm is you get e to the x over 2 sine n pi x, e to the x over 2 cosine n pi x, and then multiplying by e to the minus x, right? So all these things, three things, immediately cancel out and give you 0. So whereas you didn't have a hope of solving a PDE that popped this out for you, now with this method you do, and you get these modified functions y sub n that are still, orthogonal with respect to this norm. And if you had some initial condition f of x on like x going from 0 to 1, you would be able to write f of x equals some infinite series c sub n times e to the x over 2 sine n pi x, whereas c sub n's are calculated thusly.
And would that be a sine instead of a cosine?
Sine n pi x, yeah, thank you. Well, not the way I wrote it, so I'm showing you orthogonality. So yn and ym.
In the first sign.
Oh, in the first sign, there should be an n. Yeah, thank you. Sine n pi x.
So here, f of x is coming from somewhere else in the problem.
Yeah, you've got this problem, say, where you've got a PDE. You separate the variables. And this is the equation you get for y. And then the equation for g is always kind of like easy to solve. Doesn't have the boundary values. So you do have to solve that. You do have to get here, but that's not insurmountable. And when you get here, you'll have this setup, but you'll just have to know that those coefficients are calculated with respect to the weighted norm. Because that's how Sturm-Liouville theory works for these functions that have a weight.
So all the useful properties of Sturm-Liouville that we want are affected by the weight function.
So the question is the useful properties of Sturm-Liouville theorem that you want are affected by the weight function. So yeah, the Sturm-Liouville theorem applies equally well to this equation with the weight function if you use the weighted norm.
Right, because without e to the x, that would be 0.
Yeah. I mean, if you just looked at this original equation and solved and found functions and found eigenvalues, maybe you could formally write something down with the functions that you found, but you'd have no guarantee that it actually converged to anything or solved your problem or whatever. This way, you have like a theory that admittedly we didn't prove. This class is sort of about showing you theories and techniques, but you've got a theory now that you know will work that says, here's the new equation that I can solve. And the eigenfunctions that I get will be a complete orthonormal system, so it will be possible to write down an expression like this. It'll be guaranteed to converge in the mean square sense. So that's why it's useful. And generally speaking, if you have any function like y double prime plus a of x y prime plus b of y equals lambda times y, you can always use Euler's integrating factor trick with like mu of x equal to e to the minus integral from maybe 0 to x of a s ds. So this you learn from ODE. It's the same integrating factor.
And then you just multiply everything
By mu, yeah. You'll get that r is equal to mu. You should get that q is equal to b times mu. And you'll get that, I think you'll get that p is also equal to mu, just like we had. So this was the special case that a was -1 and b was 0. Okay, cool. So actually, I think I'll maybe stop there and talk for the rest of class about homework, but I mean, it's already 12:02. I guess we had a digression of, for classical Fourier analysis, which is fine. But still, I'll close off class and I'll stay here till 12:30 as usual for any homework help. And so I guess for video purposes, I'll stop the recording and say goodbye. But one's more than welcome in the classroom. So.